Such a fun intro every time. Welcome in, everybody. My name is Jesse. I'm here with Exploring by the Seat of Your Pants, and we've got so many of you here today. Over 400 kids from coast to coast across the continent are joining us today. Welcome back as we continue our mission of showcasing the coolest scientists and explorers on planet Earth. As you may know, everything we do is on our YouTube channel, so if you want to check out this program or like 3,500 others, you can head there and do just that. Now, last year, we did two epic series. One was with Frontiers for Young Minds, an amazing organization that pairs scientists with students just like you to write articles that students can understand, that are accessible for absolutely everyone. We partnered with them on a bevy of broadcasts. It was so much fun. And then our biggest series of the year was with the amazing folks at ifthenshecan.org. So If Then celebrates and showcases the most amazing women in science, engineering, and exploration on planet Earth. Our February series with them was one of the coolest things we've ever done. Well, lo and behold, 2024-25 get here, and those two organizations partnered on an epic series of articles. You can check them all out here. I'll get this to all your teachers. We've got so much to explore right there. And so we wanted to partner with them and showcase some really incredible people, from deep sea explorers to librarians with artificial intelligence to today on earthquake geology. Now, I'm going to welcome in Wendy in just a second, but I do want to note for our live and YouTube classes, we have a Kahoot today. So between our talk and Q&A, you can play along with a little 4-question quiz, test your understanding, and have a little bit of fun. Feel free to get that up in a separate toolbar right now. But I'm so excited to welcome back Wendy Bowen. She was the first person to join us for the If Then series last year. She's the second person to join us in our series this year, and she gets to study earthquakes and how the earth shifts and changes and moves. It's kind of a weird thought that the ground underneath our feet might not be as stable as we'd like to believe, but Wendy gets to explore this every single day in her job, and I'm so thrilled you get to learn a little bit more about our earth from her. Wendy, welcome to the program. Thank you so much for joining us again.
Jesse, and hi everybody. I am so excited to be here and talk to you about earthquakes today. So, are you ready?
Bring it up. I know you've got a lot to share with us. And while you're doing that, I'll just note too, the If Then series is here, Frontiers for Young Minds. We've got all the links for you to keep the learning going when we're done. And Wendy is like all over social media too. So I'm going to make sure you have her link to follow up more with her. But looks like we are pretty much ready to go into our
Okay. Do you see me? Am I in a
good.
trench?
You're golden. Just press hide. There you go. And now we are cooking with gas. Go for it, Wendy.
Okay, so has anybody ever felt an earthquake? I started in geology because I felt an earthquake. I'm actually from Chesapeake, Virginia. I think some of you out there are from Virginia. So Virginia has earthquakes, but not that often. I moved to California and I felt an earthquake, and that's what started me on this path. I used to be a professional actress. So you can have lots of different interests and do lots of different things in your career. But now, as an earthquake geologist, I ask different kinds of questions, like, where are the faults? Earthquakes happen on faults, so we need to know where the faults are to know where the earthquakes might be. How often are there earthquakes on those faults? How big could those earthquakes be? When are they going to happen? And what effect might they have on people and on our cities? So first, let's think about where the faults are. So the surface of the earth is covered by a thin skin of rock, almost like the shell of a hard-boiled egg. And it's broken into these big pieces called tectonic plates. Those plates are moving around over the surface, and the places where they come together are the places where we have earthquakes. You can see the outline of the tectonic plates here. See the flashing lights? Those are the earthquakes. And so you can actually see where the plates touch based on where the earthquakes are. But we need to know
We lost Wendy for a second. We're going to get her back in a second. Just before the broadcast began, she mentioned there's some people digging a pool next door that might be hitting some cables. So hopefully we have her back in just a second and can keep going in with our earthquake broadcast. So stick around, everybody. Sorry for the little bit of delay. Sometimes when you're bringing people in from all across the world, you have a little bit of a tech hiccup. While we're waiting for Wendy, I'm going to note again, if you want to check out our whole 10-part broadcast series coming, we've got 9 in the books right now. Do check out the link below. And it looks like with that, we've got Wendy back. Sorry,
okay,
folks.
sorry.
Hi, Wendy, you're back.
Okay, they're putting in a pool next door, and so our internet is going in and out. I'm so sorry. But we're talking about GPS and using GPS to monitor the motions of the ground. And so you can see these arrows are pointing in the direction the ground is moving, and the length of the arrow is showing you how fast it's moving. And so if we have two GPS stations and they're moving apart, we know there has to be something in the middle that's helping the ground to stretch. And so that something in the middle is a fault. So that's one way we can find where the faults are. But we also want to know exactly on the ground where they are so we can go and learn more about them. For that, we can use another tool called LiDAR, light detection and ranging. And basically, this is a laser, not a laser like the kind that you can cut metal in half with, more like the kind that you can use to play with your cat. So they have this laser in an airplane, it scans the ground back and forth and creates a three-dimensional image of the surface of the earth. Okay. Some of those laser light beams can actually go through trees and hit the ground, just like sunlight does in a forest. This is the kind of image that we get using that. So what are we seeing? Here's some, looks like popcorn, right? That's the tops of trees. And down here, you can see a fence line right there. And then we can even see a road. That's the flat area that's winding through here. Well, the San Andreas Fault, the most famous fault in the whole world, is in this picture, but it's under those darn trees. So we can use this technology to get rid of the trees because the laser can go through and some of the laser points, just like sunshine, can hit the ground. So here is the San Andreas Fault marked by those red lines. But don't worry, we can bring the trees back. And in fact, biologists also use this in order to study the health of different forests. Using this technology and going out into the field and looking at the surface of the ground, we were able to map all of these faults in California. There's more than 15,700 faults just in California. More than 500 of them are active, which means they could have earthquakes. Okay, so we know where the faults are, but how often are there earthquakes? How big are those earthquakes? And when are they going to happen? Okay, we can get a lot of that information from the earth itself. Rocks tell a story. And so we can use LiDAR, figure out where the fault is, and then we can dig down across the fault in order to read the story that is held in the rocks. So this is what it looks like when we dig across the fault. This is in California, Central California, along the San Andreas Fault. This is what those trenches look like from the ground. So here we are, we make the trench with the backhoe, and then we clean the trench, and then we actually take pictures of the walls of the trench, and then we very carefully map that out. We go back to the laboratory and we create something like this. So this has the mapping on the picture of the wall of the trench. But in order to be able to read the rocks and read the history of earthquakes, we have to understand some things about geology. Okay, so there's some geologic laws that help us to understand what's happened in the past. On the left-hand side at the top, there's something called the law of superposition, which sounds very boring, but we do this all the time. So imagine one of your chores when you come home is to get the mail. Monday, you get the mail, you throw it on the counter. Tuesday, you get the mail, you throw it on top of Monday's mail. Wednesday, you get the mail, you throw it on top of Tuesday's mail until Friday when you have to look at the mail. What's the oldest mail in the pile? It's the mail from Monday, right? The mail at the bottom. Rocks are the same way. The oldest rocks are at the bottom and the youngest rocks are at the top. Okay, the next law says that these kinds of rocks, like sand and dirt, sedimentary rocks, rocks that come from pieces of other rocks, they are laid down flat. And so if they're no longer flat, something has happened. On the bottom left, we have the law of lateral continuity. Sounds very official. What it means is rocks are laid down in sheets. And if they are broken up, if there's something missing, something has happened. Finally, we have something that tells us again about the ages of the rocks. And so if we look at this, this is like a mystery. You have all of these different layers, and then there's layer 4, which is cutting across. In order for layer 4 to have cut across these other layers, 1, 2, and 3, The other layers had to exist. So 1, 2, and 3 are older than layer 4. So knowing these laws of geology, let's look at this picture of the trench again. Well, we can see that these layers are no longer flat. They've been tilted. We also can see that they're no longer continuous. They're broken up. And we can see that there is a cross-cutting relationship. If you look really closely, squint your eyes, you can see that there's these red lines that are cutting across these layers. We know that that was from earthquakes on the San Andreas Fault. And so all of these little stars right here says E5, E4, E3, E2. Those are all evidence of different earthquakes. So this trench had evidence for 4 earthquakes. And based on the ages of these rocks, we can tell about how much time there was between each of these earthquakes. Okay, so now we know about how often earthquakes happen because we know how much time passed between these earthquakes. And how are we going to know how big they were? And how will we know when the next one is coming? Well, we can make a good guess, right? If we say these earthquakes happen about every 200 years and it's been 150 years, we can say there's probably another earthquake coming pretty soon. But how do we know how big they are? In order to do that, we have to have a lot of these trenches across the fault. The magnitude of an earthquake tells us how big the earthquake is, and that depends on how much fault breaks. And so if we see evidence for an earthquake at a certain time in lots of different places, then we know that it was a really big earthquake. So each one of these little triangles here, those are different trenches that we dug across the San Andreas Fault. And the different colors are telling us what the date was for an earthquake that was found in that trench. So if we look at the green ones, that's telling us all of these trenches showed an earthquake in 1812. And in fact, that earthquake was a magnitude 7.5, a really, really big earthquake. All right, so we know where the faults are. We know about how often earthquakes happen on those faults, how big they are, and when the next might occur. But what effect will earthquakes have on people and buildings? So I haven't told you what an earthquake is. Silly me, right? Okay, so as the tectonic plates are moving, they're building up stress and strain inside the rocks. Eventually, it becomes just too much for the rocks, and the rocks break. When they break, they send energy out in all directions that we feel as shaking. And so the shaking of the ground is the thing most people think of when they think of earthquakes. So this is a CCTV camera in Nepal, in a place called Kathmandu, that recorded the motion of a magnitude 7.8 earthquake. You can see people are walking, and then the ground starts to shake. And the ground actually moves so much during these big earthquakes, it's very hard to stay on your feet. You can see people are falling over, can be really scary. So this video is from another earthquake. This is one of the largest earthquakes ever recorded. It was a magnitude 9.1 that happened in Japan in 2011. It was called the Tohoku Oki earthquake. And this is a video from the airport. Strong shaking from this earthquake lasted more than 6.5 minutes. Now, shaking from earthquakes isn't the same everywhere. In fact, the magnitude of an earthquake, the distance away from an earthquake, and the local rock and soil conditions will change how much shaking you experience during an earthquake. This picture is showing how much the ground shook during a magnitude 7.1 earthquake that happened in California in 2019. This star is showing where the earthquake happened. That's called the epicenter. The areas in red and orange are areas where there was violent shaking, shaking strong enough to throw you up in the air. The areas in yellow were moderate shaking, and then the areas in green and blue experienced light shaking. But look at how the yellow goes up these valleys like this, and there's a patch of red and orange over here. And that's because of the local rock and soil. Soft soil acts like jello when seismic waves pass through it. And so you shake harder and for a longer period of time than if you were in the mountains on hard rock. There's something else that can happen during earthquakes. It's called liquefaction, and it's when the ground basically turns to quicksand. So, when you have soft sand and soil and a lot of water in the ground, the seismic shaking can push the water towards the surface, forcing the grains of sand apart and causing the ground to lose its strength. If you've ever stood at the beach or at the edge of a lake or a river in the soft soil and sand and wiggled your toes or shaked your feet, and you sink into the ground, you are creating liquefaction on a very small scale. So this can be a problem, right? If you're a house and the ground underneath of you turns to quicksand, the way that it did in San Francisco during the 1906 earthquake. We can also have landslides that happen as a result of earthquakes. In places where you have steep slopes, weak rocks, and strong shaking, you can have landslides that happen, like this one in the Pacific Palisades in California after the Northridge earthquake. Sometimes earthquakes can actually break all the way up to the surface of the earth. That's called ground rupture. Rupture something is to break it. So this house is from the San Fernando earthquake in California in 1971. At my work at the California Geological Survey, we make maps of all of these different types of earthquake hazards so that people can make wise choices about where to put houses, buildings, bridges, hospitals, and schools, and so that we can engineer those structures to make sure that they don't fall down during earthquake shaking. So on this map, this is where Hollywood is. This is where I used to live when I moved to LA. The blue areas are the mountains, and that's where we can expect there to be some landslides. The areas in green are areas where there's soft sand and soil and high water, which means liquefaction, quicksand. And then the areas in yellow with the dots in the middle, those are places where earthquakes have broken the surface of the ground before and are likely to do so again. But I've not just worked in California. I also worked in the biggest mountain range on Earth, the Himalayas. So this is the mountain range between India and Eurasia. So here's another image of that. I think it looks like a fuzzy chicken. Here's its head and its beak, and it's got some fluffy feet and its little tail. The black lines are showing a special kind of fault called a strike slip fault. So that's where one block of rock slides past the other side. I worked on this fault right here called the Karakoram Fault. So these are some geologic maps of that area. What do you notice? They don't look the same. These are all geologic maps of the same place, but they don't cover the whole area and they don't agree. And so I was like, what is going on? Why can't people make geologic maps or maps showing the geology that are the same? What's the problem? And y'all, then I went there. So this is what it looks like from space. This is a Google Earth image. And I was working inside the area of the yellow square. Now, there's a ton of super tall mountains, but if you squint, you can see these red and orange lines. Those are the boundaries between different countries. And unfortunately, these countries, China, Pakistan, and India, don't agree on where those boundaries are. And so there's a lot of fighting that goes on in this area. And so it can be difficult to get to, and it can be a dangerous place to work. Also, the mountains, when I tell you they're high, oh my goodness. Here's some pictures of what it looks like from around the area. Huge mountains that are very tall. So in this picture at the top, you can barely make out these little white things down here. Those are 2-story buildings. And at the valley floor, you're also higher than the highest peaks in Colorado. So it's already really high. And then the mountain is several thousand feet higher. So I said, oh, how am I ever going to do this? What am I going to do? And I was talking to my friend and he goes, just use the Aster images. And I said, what are you talking about? And he said, well, I work on Mars because he's super cool and he maps the geology of Mars using satellites. And he said, well, we have a similar satellite circling Earth. It's called the Aster satellite. And it can basically take what's called the spectral signature of the rocks on the ground. That's like individual fingerprints of the rocks. And using this Aster Aster instrument that's on what's called the Terra satellite, NASA's Terra satellite, I was able to take the special fingerprints of all the rocks in this area. So this is an image on the left showing what the Aster image showed me of that area. I had to get rid of all of the snow. It's called masking it so that it didn't come out because it messes up the fingerprints of water mess up the fingerprints of every other thing. But the fingerprints of different rocks are shown over here on the right. And so, for instance, there's a little pink area up here. The area of those pink rocks is this blue fingerprint. And then there's this sort of green mottled area underneath. The fingerprint of those rocks is down here. And since they have different fingerprints, I can say, okay, I know what those rocks are. So using this spectral signature, I was able to make a geologic map of the Himalayas from space. So this is what that map looks like. And by making this map, I was able to make some really interesting discoveries about the faults in the area, about how the Himalayan mountains are forming, and about what the Himalayas looked like millions and millions of years ago. So if that sounds like an interesting story to you, I would encourage you to check out the paper that we wrote about it, Mapping Rocks from Space, that's available for free in our Frontiers from Young Minds special journal article. So Jesse was just telling you about that. I hope you'll go and check it out. My co-author, Olga Tripathi Lang, and I wrote this article. We both have kids. So my kids are 10, her kids are 8 and 5. So maybe that's around your age, maybe a little bit younger. So we know that kids like this article and think it's pretty cool. And I hope you think it's cool too. So thank you for listening. And now I am ready to hear all of your questions about earthquakes. Remember, I talked about the Ridgecrest earthquake in California. This is what it looked like on the ground. This is how the ground broke and moved. This is called a mole track.
I love it. Thank you so much for ending with such an awesome picture of a cool earthquake, Wendy. That's great. And I will make sure all our classes have access to that article. Do check it out when you're done the broadcast, as well as the whole series of articles. So stay tuned for that with your teachers. What we're going to do now, before we dive in with our questions, and our North Bay crew, you guys are going to be our first question askers when we do dive in with questions, is do our Kahoot. So 4 quick questions, test your understanding, have a little bit of fun. Wendy, what you can do is help us out with hints when there's like 5 seconds left in each Kahoot answer. But for those who are new, the faster you answer, the more points you get. And what you win is Wendy and I's everlasting respect. So that's pretty cool after a broadcast like this. There's a lot of you already here. We are going to dive in just a second and have some fun together. Wendy, did we do a Kahoot the first time we did a broadcast? I don't think so.
No, I'm excited. I haven't seen this before.
Oh, wow. Here we go. I'm going to start us underway, and we'll get started in just a few seconds as it deigns to load here. North Bay is going to be first, and then Miss Coburn's Dalewood crew, you guys are going to be next for questions. All right, question 1. True or false? If the Earth were an apple, the crust we all live on would be about the thickness of the skin. So there's an apple for context. We talked about an egg as an analogy earlier, where the shell was like the crust and the yolk was like the core. What do we think? Get those answers in. Wendy, I mean, I know you live and breathe this stuff, but this is still one of the most remarkable facts I've ever learned in science. Like, it's such a neat and weird way of viewing the planet we live on. Ooh, we had a good mix in this one. But yeah, it's remarkably thin, the crust. Unfathomable. We got mostly true for that one. Amazing pandas in the lead. All right, let's go to question 2. All right. About how many earthquakes happen every year? So, Wendy, at the beginning of your talk, you had a little video highlighting how many earthquakes might happen a year. It might be more than we think. Is it 10, 100, 1,000, or over 10,000 earthquakes? That seems like a lot of earthquakes. I don't know.
I have a fun fact once this is over.
Please, I'd love to hear it. 42 answers, and there's so many of you.
3, 2, 1.
Oh, what an even split. So, Wendy,
We record more than 10,000 earthquakes a year just in Southern California.
That's insane. That's crazy. How many, do we know how many in the world? Is there like a set amount that we have a rough idea of, or no?
There's at least like 1 million every year. Japan records more than 100,000 every year.
Nice. This is like many, many a day all over that country. Like, that is hard to even fathom. So Super Cat takes her lead on a very even split. Okay, the Earth's surface is made up of gigantic tectonic plates that move and collide with one another. It might be in the picture. It might have been a main theme of the broadcast. but it's an important thing. It's so weird to think about. I think a lot of people come to tectonic plates by thinking that South America and Africa go together like a puzzle, which is how we discovered tectonic plates to begin with. But the answer for this is true. Yes. It's like, it makes it, to me, it's always made it seem like it's like less secure under my feet, the fact that the Earth's surface shifts around and moves, but the continents used to look very differently back in the day and will look differently in the future as well, which is super, super neat. All right. Super Cat keeps our lead by literally 1 point, the closest ratio going into the final question we've ever had. Now, this is a multi-select, which means it's more than one answer. More than one is going to be right. Could be all of them, could be two. Which countries below are known for experiencing lots of earthquakes? The United States, Japan, Indonesia, or Finland? Now, we covered that there's a big plate. There's a lot of earthquakes in one region of the globe. 3 of these countries are in that region of the globe. 1 is very much not. Where are we? Let's see what people got. We talked about this a second ago. When do you give them to Japan? Yes. Wow, you guys did really well. The Pacific Rim is where most earthquakes in the world happen. That's a correct sentiment. Yes, Wendy?
Yes, it is. 80%. 80% of worldwide earthquakes.
That is, I'm kind of glad I live in the Atlantic Ocean now. Third, Joyful Leopard. All right, and then we're going to North Bay. So get ready, guys. Groovy Hawk is number 2. And first for all the marbles, drum roll, please. Let's see, is Silly Alpaca. Well, way to go, guys. Thank you very much for playing along with that. That's awesome. And we are going to head to North Bay. Come on in, 3-4s, and take us away with our first question. Every live class, we're coming to you, YouTubers, you too. So share all the questions. Get ready. Hello, 3-4s.
Hi, my name's Graydon. How many earthquakes have you been in?
Graydon, thanks for your question. So the first earthquake I felt, I was actually in 3rd grade in Virginia, and it was very small, and I didn't know it was an earthquake until later. And then I've probably been in 30 or 40 earthquakes, and I think 3 of them have been larger than a magnitude 7. So when there's an earthquake, there's a lot of smaller earthquakes that happen afterwards called aftershocks. So I'm not counting those. I'm just talking about sort of individual earthquakes that happen on their own.
That's wild. I really, like, to me, when I hear 7 as an earthquake, I'm like, holy, that's a huge earthquake. You've been in that
It
many?
is
That's
huge.
crazy. Wow.
Yeah, on average, there's about 15 magnitude 7 earthquakes that happen somewhere in the world every year. And since I work in places and study places where there are lots of earthquakes, my chances of being in those earthquakes go up.
Very cool. I will say I went to Japan over the summer, and I was probably the only person that went there kind of hoping for like a slight earthquake, and we felt nothing. It was dead. Those 100,000 that happened there didn't happen where I was. Ms. Coburn, Dalewood School, come on in, unmute your mic and take us away. Hey.
Hi. So we're a remote class. Our kids are at home, but we have a couple of questions for you. First of all, we'd like to say the graphics were phenomenal. For our visual learners, we really learned a lot. It was great. It was easy to follow. So Wendy, thank you so much for that.
Great. Glad to hear it.
Yeah. So John in my class or Alexis are going to throw their mic on and ask you a question.
How is food to help explain ecosystem interactions?
Oh, Ms. Coburn, could you repeat that for us really briefly?
Actually, John, can you repeat that again? You're good at it.
Hey,
How
John.
is food used to help explain ecosystem interactions?
What was the second thing? How is what?
How is food used to help explain ecosystems?
Oh, good. So we're talking about, we're learning about ecosystems and how earthquakes are affecting our food. So when they farm, right?
Yeah.
And how does earthquakes come into food distribution and how does it affect it?
Neat.
Okay, that's an interesting question. I don't think I've ever had that question before. So there's a few things. Earthquakes can actually, or faults can change where the water is, because when earthquakes happen, they grind up the rocks in the fault zone, which allows water up and down inside the ground. And so if you're in the desert, you'll often see lines of palm trees and oases along the fault zones. And so some of that can be used, I assume, for farming. But what earthquakes can really do is impact the supply chain. So for instance, in California, we grow a lot of food, but we also have a lot of active faults. And the San Andreas Fault a lot of important systems like ports and harbors and that take and distribute our food, and also the roads that take food to different places, can be broken and disturbed during the fault. And so that can change how we get food to the people that need the food from the places that it's grown.
Great answer, Wendy. That was fantastic. Miss Collins' class, Jerusalem Elementary, come on in, unmute your mic, and we will come to you guys next. Hey, guys, welcome in.
Why do some earthquakes happen? Why do a lot of earthquakes happen in specific places?
That's a great question. So most earthquakes happen in places that are near the fault, the plate boundary. So the places where those tectonic plates come together, they're sliding and moving around, and that causes the stress and strain to build up, and that's what causes the earthquakes. So most earthquakes happen around the edges of the plates.
Yeah, great question, guys. One of the fundamental things in earthquake geology is that plate tectonics. It's one of the things that allowed us to understand plate tectonics to begin with, is that earthquakes and volcanoes are so concentrated in those regions. So good thinking, guys. 2A04, we're going to head to you guys. Unmute your mic. Come on in and take us away. Hey.
What causes liquefaction?
Causes liquefaction?
What causes what?
Liquefaction or liquefaction? Is that the
Liquefaction.
again.
Yeah. Excellent question. So when you have soft sands, imagine you have a lot of sand, okay? And then there's water in the ground underneath the sand. And when you shake it, that pushes the water up. And when the water moves up, it pushes all those little grains of sand apart. And when all those little grains of sand are no longer connected like that, when they're apart, they can move around a lot. And so that causes the surface to lose its strength, and things can just sort of sink in to the ground. And it's called liquefaction. I think of it like quicksand, but quicksand that only happens for like a moment while the shaking is happening.
I don't like quicksand that lasts longer than that, so that's very comforting. By the way, I love the demo like this, and I do encourage you have some fantastic social media things on Instagram, Twitter, everything. Dr. Wendy Rocks. Do check out Wendy's stuff, because there's a lot of cool stuff to explore and discover there as well. Miss Lou, I'm coming to you in a second, but we've had a question on YouTube a couple times, so I want to get it in. Can an earthquake crack a mountain? Basically, could the ground break go up straight through a mountain and split it in half? Is that possible, or something that we've seen?
That's a great question. And fortunately, the answer is no. When earthquakes happen, they don't split the ground apart. So I want everybody to do something with me. Okay, let's snap. Everybody snap. What happens when you're snapping? Have you ever thought about it? You're putting the two surfaces of your finger together and you're pushing, right? You're putting energy into that. You're pushing, and then eventually it moves. When it moves, that movement releases energy that we hear as sound, right? It releases waves that we hear as sound. What happens if you don't have your fingers together? There's no sound. There's no energy waves. How does that relate to earthquakes? Well, earthquakes have two pieces of rock, right, that are pushing together, stress and strain build up, bam, it happens, and we feel that energy is shaking. Sometimes we even hear it as sound too. But if the fault is not pushing together, if it's apart, there's no earthquake, there's no waves. And so the ground doesn't open up. That started as a myth because of those secondary effects of earthquakes, like landslides. And so when you have earthquake shaking, steep slopes and weak rocks, that can cause the ground to move. And then it looks like there's cracks in the ground, but that's not the fault. That's just motion of other parts of the rocks around the fault.
Very cool demo, and I love when I get the chance in the background to see like 100 kids all snapping together. It's like West Side Story. That was fantastic. Miss Lou's class, we're gonna head to Milton. Come on in, guys. Miss Barajas, you're next. Miss Digby, there's so many of you, like 400 kids. It's crazy. Grade 5s, come on in. Take us away. Hey.
Can earthquakes cause other natural disasters?
Ooh.
Absolutely. What a fantastic question. So when earthquakes happen underneath the ocean, like a particular kind of earthquake where it goes up like this, that pushes all of the water above the fault up. That water then flows out in all directions, and that's what causes tsunamis. So earthquakes can cause tsunamis to happen. They can cause landslides to happen. So sometimes earthquakes can even cause volcanic eruptions. But more often than not, the magma moving through the ground causes the rocks to crack and vibrate, which we call earthquakes. And so volcanic eruptions can cause earthquakes, and sometimes earthquakes can cause volcanic eruptions by sort of changing the underground plumbing. So it can go both ways. So yes, absolutely.
Very, very cool. And I'm realizing as you're saying this, that our kids, pretty much everyone today, in fact, all of them weren't even born when this happened. But the biggest natural disaster in my lifetime was earthquake that caused a massive tsunami in Indonesia and in the Indian Ocean. So this is the costliest, biggest natural disaster ever. And we've reached cat part of the broadcast. There's a cat that enters into every video call, whether or not someone owns a cat or not. It's like black magic. It's amazing.
Yes.
Mr. Ross, let's go to California. Come on in and take us away. Hey, guys.
What would happen if an earthquake lasted half an hour?
Ooh.
That's a really good question. So earthquakes unzip like zippers. They start at one place and then they unzip along the fault. So it doesn't just break all at once. And so the length of the fault, imagine you're trying to unzip the zipper on your jacket, right? That's going to take just a particular amount of time, not too long. But if you're trying to unzip a sleeping bag, that's a lot more zipper and it's going to take a longer amount of time. So the longer the fault that is rupturing or breaking, unzipping, the larger the magnitude of the earthquake and the longer you're going to feel shaking. Fortunately for us, there are no faults on Earth that are long enough to last for half an hour. I think the longest amount of shaking is probably about 9 minutes, and that was from an earthquake that happened in Chile in 1960.
Yeah, very cool. We've never had that question before in any Earth-related broadcast, so thank you so much for that, Ms. Barajas' class. Ms. Digby's class, we're going to head to Fairfax, classically the high school class with the best questions I've ever had in the history of Exploring by the Seat of Your Pants. So come on in and take us away, and we'll see if we can sneak in some more before we have to wrap up in a few minutes. Hey, guys.
Can you hear us?
Yeah, you're good.
Okay. Why was there an earthquake in Virginia even though we're not near a fault?
Yes.
Such a good question. The Mineral, Virginia earthquake happened on August 23rd, 2011. It was a magnitude 5.8. So Virginia, all of the East Coast, all of the Midwest, everywhere on Earth actually has ancient faults because plate tectonics have changed through years and millennia, right? They're slamming together, pulling apart, new land masses are created, some land masses are destroyed. But whenever things collide, the rocks break. So there's ancient faults under Virginia, under all kinds of places. And so they're storing up stress too, but just at a much slower rate than places that are along the edges. And eventually those faults are going to break in earthquakes. And so the Mineral, Virginia earthquake was one of those earthquakes. There was a magnitude 4.8 in New Jersey last year. I don't know if you guys felt it. I was in Maryland then. I felt it. Charleston, South Carolina had a really huge earthquake, magnitude 7+ earthquake in the 1800s. And in fact, the largest earthquake sequence to ever happen in the United States happened in Missouri. So earthquakes on the East Coast and Midwest are rare, but they do happen. I have a series on TikTok that's earthquakes in all 50 states. So you can check that out for your state. I'm only up to Illinois though. So I'll get to Virginia, but it's going to take a minute.
Wendy, it's, we get a lot of questions in these broadcasts, but the fact that you knew like the magnitude and the date of the earthquake in Virginia offhand is like next level. That is fantastic. So thank you for that. That's some special knowledge. Guys, there's so many of you. So what I'm going to do is encourage all our classes. Email me more questions. Wendy's amazing. We're going to try and get you as many answers after the show as we possibly can. We're going to take 2 more live. I'm picking at random, so don't take it personally if I don't come to your class, but thank you all for your epic amounts of enthusiasm, and trust me, there'll be lots of opportunity to keep the learning going when we're done. So I'm going to head to our 2A04 crew. Come on in if you want to unmute your mic and take a second question for us, and then I will go back to Ms. Digby's class because it's pretty rare we have some high schoolers in. I'm curious for their questions. So, hey guys, welcome in.
What inspired you to not become an actress and become like an earthquake geologist?
Amazing.
That's a great question. So I always liked science, but I saw myself as an actress, as an artist. I played the guitar. I like to make pottery. I like to write poetry. And so I always thought science was interesting, but that wasn't my vibe until I moved to Hollywood to be an actress, and I was doing that. And then I felt the Hector Mine earthquake. It was a magnitude 7.1 in Southern California. And it was like terrifying, but so exciting. And so it piqued my curiosity. I wanted to know more. I wanted to learn more. And once I started working at the USGS, which is an government organization that studies earthquakes and other hazards, I realized that I could use my background in theater in order to communicate well with the people who needed to know things about earthquakes, right? Because earthquakes can be really dangerous. So it's important that people understand earthquakes, that they know what to do when they feel an earthquake. And I saw an opportunity for me to use both of my skill sets and to really learn more about the world around me and to engage my curiosity. And so I'm going to use this opportunity to tell you all that this week is the largest earthquake drill in the world. So October 17th at 10:17 a.m., everybody's going to practice the recommended action for staying safe during earthquakes, which is dropping down to the ground, taking cover underneath a sturdy object, and holding on until the shaking has stopped. So you can learn more about it. It's called the Great Shakeout. And if you can, I would encourage you to take part. I'm going to be on TV all day that day. So if you're in California, watch TV. You'll see me.
Wendy, that's awesome. I'm going to make sure all our kids have that. That's one of the coolest backstories ever. Incidentally, like that would make a good movie, in which case you could come back as an actress and play yourself in the movie. I'd watch it. That sounds pretty cool. I'm just saying. Wendy, we've got time for one more live question. Classes, please do email me more after the broadcast is done. You all have our email. We'd love to hear from you. Miss Digby's class. Oh, are you still around? Let's check in with our Fairfax class for one more. Hey, guys. Are we there? Maybe you're a black screen. That's okay. We're going to head to California instead and go to Miss Baraja's class. Come on in and take us away, guys, and we'll wrap up with you. Do you have a final question for Wendy?
What will happen if an earthquake hit a volcano?
Yes.
Well, that's a good question. So it depends. Sometimes earthquakes happen around volcanoes and there's nothing going on. Right now, there is an earthquake. I think it's Mount Adams. A volcano that's having a lot of earthquakes. And what that's telling us is that magma is moving around in there, or superheated gas, maybe hot liquid. It's hard to say, but the rocks are cracking and vibrating. But for instance, I was working in Guatemala last summer, and there was a pretty big earthquake that happened near a bunch of volcanoes, but it was not related to the volcanoes themselves. And you know what happened? Nothing. So sometimes earthquakes happen without interrupting the volcanoes, which is really good because earthquakes are dangerous, volcanoes can be dangerous, and when you put them together, that's a double whammy situation, right? So just depends.
I love the way you think in that class because my mind is always like hurricane tornadoes and like lightning earthquakes. It's very much fun that way. Natural disasters are dangerous and something worth preparing for, like our Great Shakeout, but very, very cool, we have to admit, and that's why people like Wendy get the chance to study them because they're amazing natural phenomena. Wendy, time flies when you're having fun. I wish we could go all day, but I'm running to another broadcast in a minute. So I want to highlight the Epic If Then series. So much to discover. Wendy's awesome articles right here. Frontiers for Young Minds websites. If Then She Can's website is amazing. And on TikTok, you're not just Dr. Wendy Rocks, you're Dr. Wendy Rocks It. I'm not wrong? Yes?
That's right.
Check
That is
out on
correct.
TikTok. Earthquakes in every state. Anything you want to find out more. Thank you so much. And before we bring in our kids to say a big thank you and farewell, is there any last message you want to leave our classrooms with today?
Yes, it is that if you have lots of different interests and you don't know what you want to do, that's okay, right? You can do lots of different things. You can try lots of different things. And if science is something that you're interested in, you should give it a try. It's a lot of fun.
Wendy, there's no better message than that. I hope our class will take the chance to let us know what you think of today's broadcast. I'll email you all sorts of cool stuff in a minute. But as we do to wrap up every show, I'm going to bring in all you classes to join me in saying a big thank you and farewell. So our North Bay crew, Miss Coburn, Miss Cullen's class, 2A04, Miss Barajas, thank you so much, everybody.
Thank you.
Thank you.